Okay, so welcome. I'm glad all of you, those of you here are here because I wasn't sure how many people are around in summer. It gives me great pleasure to welcome Vishnu Ratnam. He has finished his PhD. He's actually defended his thesis, he said, from electrical and computer engineering, or it's electrical engineering at USC. So he's going to talk. This is, I assume, your work for your PhD thesis.
Well, right? It's actually around 30% of the work, so the last 1 year, but yeah.
Very good. So anyway, he's going to talk about channel estimation and beamforming for massive MIMO systems. And this is of great interest to us here at WINLAB, given that we are started on the Cosmos project, right? So let's hear what Vishnu has to say.
Thank you. Thank you, Vishnu. Thank you for the introduction. So essentially today I'll be talking about a small portion of the work I've done during my thesis. This is actually very recent work done over the last 1 year or so. So you won't find any of this material online yet. I mean, the papers have been accepted, but they're not available online. So what I'll be talking about today is a bunch of techniques for doing channel estimation to adapt your beams towards intended directions. That can be done using only analog components or only analog processing. Okay, so I'll start off with a brief introduction. This is something we already know. Today wireless data demand is increasing and it's ubiquitous, but because the spectrum is a limited resource, you want spectrally efficient techniques to communicate, right? MIMO systems, where you have multiple antennas either at the transmitter or receiver or both, is one good way to increase the spectral efficiency. Why? Well, such MIMO arrays can give you two kinds of gains. Firstly, when you have a large antenna array, you can direct the power that you transmit in intended directions, which improves your link margin or improves your SNR, or what is known as the beamforming gain. You can point beam towards intended directions. And another bigger advantage is something called multiplexing gains. Essentially, on the same time frequency resource, you can communicate to multiple users by essentially pointing beams such that they don't interfere with each other. Okay, so because of these advantages, MIMO is one of the key focus areas for next generation cellular systems. And with progress in algorithms and hardware and technology, systems are rather moving to the massive MIMO regime, where you could have 100 to 1,000 antenna elements. Okay, at the base station and at the user, you could have, let's say, 32 antennas or something like that. This is even more popular for millimeter wave systems because at such high frequencies, you can actually pack a large antenna array on a small form factor. So you can make it fit on a phone or a base station. Right, so the good thing about massive MIMO, when you increase these antennas to these large numbers, is that the beamforming gain that we talked about, that increases your SNR, that increases. The number of users you can communicate with simultaneously increases, and the pre-coding at the transmitter becomes very simple. I mean, you can show that linear pre-coding becomes capacity optimal. But one big disadvantage with this massive MIMO is that the implementation cost and energy consumption goes up. Let's talk about that briefly. So antenna elements themselves are affordable, so you can have a large array of antennas at either your base station or on your mobile phone. But the equipment that sits behind it, that we will call the up-down conversion chains or RF chains, these include components like your ADCs, DACs, power amplifiers, mixers, and so on and so forth. These are what are expensive and power hungry. So when you're talking about these massive arrays, feeding each antenna with a dedicated such up-down conversion chain is rather impractical. And so as a solution to this, reduced complexity transceivers have been proposed in literature. Okay, what are reduced complexity transceivers is that you reduce the number of these up-down conversion chains. So you use a fewer number of digital data streams, use these chains to convert them to analog, and then you do some sort of signal processing in analog so that you can feed them to the multiple antennas and still avail many of the benefits that a large antenna array offers. For example, if you have a single digital stream, you convert it to RF, and then you can use a bunch of phase shifters here to feed a phase shifted value of the signal at different antennas such that you can still create a beam with the full beamforming gain. Right? So how do you do this analog processing? You use analog hardware such as switches and phase shifters and so on and so forth. So the intuition, or rather the premise for this design, is that these analog hardware components like switches and phase shifters, they are cheaper and more power efficient than full digital transceivers. Right? And therefore, these sort of schemes make massive MIMO more practical. Okay, so there are many types of these reduced complexity transceivers that have been proposed in literature. In fact, work on this has started long back in 2000 to late 1990s, early 2000s. Okay, something called antenna selection, where you use a switch bank to just switch between antennas. There's something called beam selection, and one that's popular more right now is something called hybrid beamforming. Okay, in fact, a significant portion of my thesis that I will not be talking about today was on one such hybrid architecture called hybrid beamforming with selection, where you use a combination of both phase shifters and switches to improve your beam shaping capabilities and do better multi-user simulation. Okay. If you're more interested on that, we can talk about that offline or after the talk. But going back, there are several kinds of reduced complexity transceivers that have been proposed, and the advantage is that they make massive MIMO practically viable. Why? Because they bring down cost and power consumption. The disadvantage is that the channel estimation overhead, the cost for learning the channel, increases. Let's talk about that why. By the way, if you have any questions, feel free to interrupt me in the middle of the talk.
So I have a question to Ivan, actually, related to what you just said. So our platform, the Cosmos platform, what is it going to do in terms of techniques that he's talking about for selection?
So it is hybrid beamforming, right? It has two modes. One is where you have a single beam with all 64 elements, no polarization, where you're just steering the beam, right? So this is literally just fairly straightforward.
Right.
The other, and of course, then you have a problem of searching, right? How do you find out where and what, right? The other one is you have 8 beams, which are much coarser, of course, but you can have 8 simultaneous beams. So it's either one beam aimed at one direction, right? Fairly narrow, or 8 beams that are aimed in some number of directions, much less, much coarser, right? But you can do, they're much wider beams.
Now for the selection, what is the feedback that we need?
So that's a good question, right?
Right. So what is the feedback that you assumed in your hybrid beamforming?
I
know you're not talking about it today.
Right. So here what we assume more of a TDD sort of a system. So you do uplink training to do channel estimation, and then you do build the beams. So we use two kinds of channel information. One is more coarse and one is more fine. So what you do is, to build the beams, you use average channel information such as the power angle spectrum, so on and so forth. The argument is that these on an average stay constant for a longer time duration. So this you can learn with a relatively low overhead. So you point beams based on this, and once you point beams, now you are only concerned with the channel within that beam span. Right? So you are spanning the subspace of the complete channel using average information. And now you are learning the actual instantaneous channel only over a small region of that space. And that you do using uplink train. So you don't use a feedback. Yeah.
So no, we can't change the configuration of the array, right? So essentially, once you aim the beam in a particular direction, so you can go from one mode to the second, right? You sort of say, okay, I'm going to use all 8 beams, find out quickly where somebody is. An assumption, of course, is that when you're doing that, your hardware for, say, calculating the energy is much cheaper than if you put the full RF chain on it, right? Which, of course, is debatable.
Right.
In our case, we have 8 RF channels, right?
Mm-hmm.
So, you're already way beyond the power budget that you have. But, you'll figure out which direction, which principal direction, and then the only thing you do is you carefully steer the beam based on mobility, right? That's pretty much all you can do in the array that we have. You can't change anything on the phasing or amplitude of the individual.
Okay, all right, please go ahead.
Yeah. So one of the main issues is how to point the beams. That's what I meant earlier. The channel estimation overhead increases. Okay, so let's talk about that briefly. So any kind of beamforming that you want to do, let's say at the receiver, you require some kind of knowledge about the channel. You need to know where are the directions the power is coming from, so that you can point beams in those directions, right? How do you do that? Well, typically one of the common ways is to do pilot translation. You send a known signal from here, whatever you receive here, from that you want to estimate what are the good directions to point my beam. The issue is when you have a fewer number of these digital chains, you are only able to observe a sub-dimension of the channel at a time. Okay, think about it in the form of I have only one ADC here. That would mean I am only able to observe the channel from either one antenna or one direction, where the direction is defined as how that linear combination of antenna of phase shifter components turns out. Okay, so the channel, you can think of it as a n-dimensional space if you have n antennas. So you're only able to observe channel in one dimension of that. So what you would have to do when you have fewer number of these RF chains is you have to time multiplex them across your different antenna dimensions, and therefore you need to transmit multiple pilots, one pilot for each allocation of the RF chains to the antenna dimensions, right? So this is bad. Why? In fact, so if you're doing this sort of a procedure, and if you do exhaustive channel estimation, which means you want to learn the full channel, then the overhead for learning the number of pilots that you have to send can be of the order of the number of transmit times receive antennas. Why? Well, think about it in this way. You pick one beam at the transmitter and then you beam sweep at the receiver. You pick the next and then you sweep, next and you sweep, so on and so forth, right? So this overhead can be pretty large when you're talking about a massive antenna, because you could have 100 elements here, 30 elements here. It's already a huge number. This is clearly bad. Why? Because when this overhead is large, the latency goes up, throughput goes down, and something called initial access, where a base station and UE discover each other, and to timing and frequency synchronization, that becomes more complicated as well. Okay, so this problem is not new. A lot of people have realized that, okay, this channel estimation is a big issue, and several fast channel estimation algorithms have been proposed. Okay, I'll briefly discuss some of them, assuming the number of transmit antennas is one, just for convenience. Okay, so we are estimating at the receiver. So one technique is called iterative beam scanning. This is like binary search, essentially. Instead of picking narrow beams and trying to sweep, you pick two fat beams, see which is giving you most power. Now you use half that beam width and then search within that, and so on and so forth. You keep reducing at each stage the narrowness of your beam and search till you find the optimal value. Right? So instead of order of mRx, the overhead becomes log of mRx. There are several other techniques. Another one is something called sparse ruler based sampling. Here what you are doing is you are trying to estimate the covariance matrix, spatial covariance matrix of the channel at the receiver. And if you have some nice structure at your receiver, like you have a uniform linear array or a uniform planar array, so there is some nice structure to it. Why? Because the correlation between antenna 1 and antenna 2 is probably same as antenna 3 and antenna 4, because the spacings are same. So you have a nice triplet structure for the covariance matrix. When you have that, you don't need to sample at every value. By doing some sparse ruler based techniques, you can bring down the overhead to square root of number of antennas. And then there are compressed sensing based techniques. These exploit the fact that channels are mostly sparse, especially at millimeter wave. So in that case, when you only have a few number of paths, then you can exploit the sparsity to reduce this overhead. Okay, so let's briefly talk about the issues with these schemes. Firstly, all of these schemes assume that you have prior timing and frequency synchronization. Okay, they assume that your transmitter and receiver are synchronized in time and in frequency. Or they would need this synchronization to be done without the beamforming gain at the transmitter and receiver. So in that case, you're operating at very low SNRs, and there doing timing and frequency synchronization is more complicated. Secondly, some of them, like these sparse ruler based techniques, are only applicable to certain array configurations. They cannot be used more generally. And many of these schemes require that the channel remains static during this whole estimation phase. Note that there are multiple pilots, and then during each of these pilots, the channel should not change significantly. And another thing is they are prone to the transient effects of beam switching. Now, note that in all of these schemes, you have to actually switch between different beams. Okay? Whenever you are doing beam switching, note that these beams are being created by analog hardware, which will inherently have some transient effects. So either you have to switch slowly enough such that these transients go away, or you have to live with them. Both of them are bad, because if you switch slowly, you're eating into the overhead, you're increasing your overhead, and if you switch fast, then you have to deal with the transients. Okay? And as you can notice, the overhead still remains a function of the number of antennas. Right? Why? Why is the overhead still a function of number of antennas? Is because conventionally channel estimation is something that we consider has to be done digitally. You send a pilot, you sample it using an ADC, and then you do some digital signal processing to find out what the channel information is. Right? Right? Now, because you have very few ADCs, you cannot get past the fact that you have to time multiplex your ADCs across these antenna dimensions. Right? So, here is one question, is that suppose you can do channel estimation in analog, okay, without using digital hardware. If you are able to do that, then you actually no longer care how many ADCs you have. You could make the overhead for learning the channel order of 1. You don't care how many antennas, you don't care how many ADCs. It no longer depends on that, right? So this is what will be the focus of this talk. How can you acquire enough information about the channel in analog to be able to point beams in desired directions? Okay. So let me give you a brief example of how this could work. Okay. This was actually a concept that was used very early during the 1960s and 70s for space communication. It's a very naive approach. Of course, what we'll be doing is something much more complicated, but it gives you an idea of how things work. Okay, it's something called adaptive antenna arrays. So think about it in this way. Think about that you don't have multipath. There's a single path channel between the transmitter and receiver. Okay, and we want to do channel estimation here so that you can point the beam. And consider you're sending an amplitude modulated signal. Okay, and which is like m of t cos 2 pi fct. Where m of t is your message signal, and the received signal at the antenna I is yi of t is m of t cos 2 pi fct plus theta I, where theta is nothing but the phase shift that the ith antenna encounters in comparison to the first antenna. Right? Now, let's say at each antenna you can somehow also recover the carrier signal using something called a phase lock tool. Okay. So at each antenna I, you have access to Ci of t, which is nothing but the carrier component of this, which is cos 2 pi fct plus theta. If you use that to convert your received signal to baseband, it's simple trigonometry. What you get here is this times this, low pass filter, what you get is m of t over 2. Right? And then you can just add all of these components in phase. Essentially, what is happening here is you are able to combine the signal from different antennas in phase, even though they are not arriving in phase at the different antennas. Right? In other words, you are actually creating a beam in that direction. Because what is beamforming? Beamforming is exactly the same as trying to combine signals from a particular direction in the correct phase. Right? So we are able to do coherent combining without explicitly doing channel estimation. Well, it's not that we are not doing channel estimation. We are still doing channel estimation, but it's actually happening in analog. The PLL is doing it by indirectly estimating theta angles. Now, this is a bad architecture. Firstly, you need a PLL for each antenna. It's something that's not feasible. And firstly, this only works for a single path channel. What happens when you have multipath, right? So, but this gives you a flavor of how these architectures can work. And the architecture that I'll talk about has some similarities to this. And it also helps you appreciate the fact that these things can actually be built because there were actual satellites that were built based on this concept. Okay, so as I said, this only works for single path channels. And secondly, they don't exploit any of the properties of massive antenna arrays or millimeter wave channel properties. Okay, the overview is something like this. Firstly, I will talk about what is the channel state information that you need to design a good beamformer. Then we can talk about okay, this is the CSI required. What can I do in analog? Then I'll talk about one such analog channel estimation technique called periodic analog channel estimation. And then I'll talk about its limitations and some future directions. Okay. And if we have time, I will discuss about two other schemes. Okay, this is the brief system model. Consider you have a single user scenario where the transmitter has a single antenna and the receiver has multiple antennas. Okay, this is just for simplicity. The results can easily be extended to a multi-user case where you have multiple antennas at the transmitter. Okay, we assume a low complexity receiver where the receiver has MRX antennas and a single digital chain. Okay, as I said before, the extension to multi-user case is straightforward. So the channel from this single antenna to this multiple antennas can, at a frequency f, can be represented as a MRX cross 1 vector that has 3 components. Okay. Now this is in frequency domain. Here throughout this talk I will be talking about channel in the frequency domain, not in the time domain. Okay. At frequency f, the channel has 3 components. Okay. It's a summation over L multipath components. So there are L echoes from different reflections. And then there are three contributions. Alpha L is the amplitude of the Lth path. This quantity is the phase shift that this path takes from this antenna to the first antenna here. Okay, and this is a vector that corresponds to the additional phase shift that you encounter to different antennas. Okay, so there are three components. Firstly, the amplitude of the path. Second is the phase of the path from here to the first antenna, and this is the inter-antenna phase shift. Okay.
So, question. You're assuming that each of these antennas will essentially go to the same path, right? Because if there is only phase shift,
Right.
you're assuming that alpha L does not depend on the antenna,
Oh yeah.
right? Just
Right.
Okay, that's-
Is there a or
I mean, if you look at the geometry, right? That's not the case, right?
why not?
Well, I can give you pathological cases if I put something in front of one antenna.
Right.
I mean, and of
Yeah.
course now you extend that to
Yeah.
whatever is
Yeah.
between the,
Yeah.
right? So it's not, in general, it's not the case.
Right. Okay.
Right.
Yeah.
But I mean, that's just a question.
Yeah.
It's not clear how much that has
Yeah,
an impact.
yeah.
Right?
So anyways, this is the model we use. So h of f has this three L components. Okay. So the received signal at these antennas is nothing but the channel at that frequency times the transmit signal at that frequency. Okay. Because you have this reduced complexity architecture, here this is not what you receive. What you receive digitally is y of f, which is nothing but t conjugate transpose times this received signal. What is t? T is a vector that represents what this analog processing block is doing. Okay. Let me know if something is not clear at any point. Yeah. So this is just repeat of that from the previous slide. T is that analog processing or this beamformer represented as a vector. This should be f times s rx of f is what y of f is. So this is the question that we wanted to answer. What is the CSI that you require to build this beamformer T? Okay. So if you want to build the optimal beamformer, well, that is straightforward. T as a function of f should be actually a scaled version of the channel at that frequency if you want to do maximal ratio combined, right? Why? Because then this L2 norm of this quantity is maximized. Okay, so to build this kind of optimal beamformer, what do you need? You need to know h of f for each and every frequency f. Acquiring this kind of information in analog is something that's going to be very, very hard. Okay, so we do a compromise. Let's say I don't want all of h of f. Let's say I only want to acquire h of f for some center frequency h of fc, and then I build this beamformer T using that, and I use it for the whole band. How bad can you do? Okay, that's the question. Well, if you have a single path channel, if there's no multi-path, it actually works amazingly well. Why? Well, h of f, if you can remember from the previous slide, now it only has one component, this is the amplitude, this is the inter-antenna phase shift, and this is the phase shift curve to the first antenna, right? So the dependence on frequency is just a constant complex number that's constant for the whole vector. So in other words, the dependence on h with frequency is very minimal. So a beam that you design for one frequency fc is also correct for other frequencies. In other words, if you have only one path coming from there, and then for the whole frequency band, I just point a beam in that direction, and that's correct for everything, right? Okay, so that works very well for single path channels. What about multi-path? Okay, let's take a simple scenario. Let's take a two-path channel. This is your receive antenna array. There's one path from here and one path from here. These are those quantities that we talked about before, channel quantities. Okay, at frequency, the center frequency fc, the channel has again two components, these two. Okay, at frequency fc plus fk, some offset, you have the channel looks slightly different. Okay, so these phases are different. So what did we want to do? We said that we want to build a beamformer with this information and use it for the whole frequency band. So let's see what happens if we build a beamformer with this for this. So if you do that, you get the inner product of this with this. So you get all signs of cross terms, all kinds of products here, right? But here we exploit the fact that these array response vectors, which are these inter-antenna phase shift vectors, for paths that are sufficiently far apart, they are near orthogonal. Okay, so the product of this and the cross products, they become very small numbers, and those you can ignore. So what you end up with is just this times this times this times this. So it looks something like this. Okay. Well, this was if you use the wrong beamformer from a different frequency. What if you use the correct beamformer value? You get this times this and this times this. You get something like this. Now compare this to this. What do you see? You see that these two are same as these two. There's just a phase shift. These two are same as these two. There's just a phase shift. Okay. What's happening? What's happening is this. When you're doing this kind of beamforming from a different frequency, and there are two paths, you're actually building the correct beam in this direction. You're also building a correct beam in that direction, but you are not adding the contributions from this path and this path in the correct phase. Okay. In other words, more intuitively, if I have a path arriving, a reflection from that wall and a reflection from that wall, the directions of these paths would remain same over a wide frequency band, right? So for one frequency, if I design a beam like this and a beam like that, that would also be correct for the other frequency, but at the different frequency, the phase of this path and this path are different. So you're amplifying the signal from here, you're amplifying the signal from there, but you're not adding them up in the correct phase. So the claim of this talk will be that as long as the channel bandwidth is sufficiently wide, the loss due to this incoherent combining is small. Why? When you have a wide band, there will be some frequencies where they don't add up, they add up destructively. There will be a lot of other frequencies where they add up constructively. So you'll have a frequency selective fading sort of a scenario, and when you average, we show that the performance loss is not significant. Okay. So that's what we will be doing. We will be trying to estimate h of fc for one frequency in analog and then use that for doing beamforming. Okay, so here comes to periodic analog channel estimation. So from the transmitter, you actually send two kinds of symbols. One is called a reference signal and the second is data symbols. Okay, so data signals you can ignore. These are like OFDM transmission, conventional OFDM transmission. The reference signals are what you send to acquire this channel knowledge in analog. Okay, what you can see is that it's just a pure sinusoidal wave. So this is what the transmission structure looks like. There is something called the initial access phase that you can ignore for now. Okay, this ABD is the analog beamformer design phase. This is where you want to learn the channel to build the beams. Okay, this is the phase that we are interested in. Once you are able to build the beams, then you do data transmission, then you again adapt your beam to data transmission and so on and so forth. So during this phase, you only send these sort of reference signals for estimating the channel and pointing the beams. Okay, so let's focus on this analog beamformer design phase. And you're sending a reference tone like this. Okay, so you're sending this. When you send a signal like this and it passes through the channel, what you receive at the nth receive antenna is nothing but the same sinusoid but magnified or scaled by the channel coefficient and rotated in phase by the channel coefficient at that frequency. Right? So it's just the transmit signal rotated in phase by the channel coefficient and magnitude. Yeah. Then you have some noise. Let's say the receiver, somehow you have an access to a sine and a cosine of this center frequency Fc. Let's say an oracle gives you this information. Okay. Then what you can do is you can multiply your received signal with this sine and cosine. Okay. And if you integrate over a symbol duration, what do you get? You get a quantity that's proportional to the real and imaginary components of h of Fc. This is what we wanted. We want to estimate it, h of Fc. Right? So what this says is that if you somehow have access to a sine and cosine of this frequency, you can actually use that to estimate the channel in analog. And that's what we'll be doing. Somehow using some block components that I'll be talking about later, we will try to estimate, you will try to obtain a sine and cosine of Fc. We will use that to multiply and integrate with the received signal to actually get a quantity that's proportional to h of Fc and use them to update your phase shifters. Okay? Yeah. So this is what the receiver architecture looks like. There will be a block called the PLL, I'll talk about it more, phase block loop. It uses inputs from one or more antennas to estimate a sine and then its pi by 2 version cosine, okay, of Fc. You multiply the received signal with those sine and cosine, you integrate, or you essentially do a low pass filter, and whatever you get at the output, you use them to update your phase shifters at different angles. Okay. So here was the first part where we wanted a sine and cosine of Fc. Okay, we need to recover this. Now, why is knowing Fc not sufficient? Well, you can claim that it's a reference signal, I know the frequency FC. Why do I need to recover it from the transmitter? I can just produce it at the receiver, right? The reason that won't work is that these oscillators typically have inaccuracies, right? It could be 50 ppm, parts per million, and at 30 gigahertz that could be a large number, several megahertz of offsets, right? So you will need a way to actually match the frequencies correctly. So you have to recover it from the transmit signal, okay? So we do that using something called a phase lock loop. Okay, let's assume that at antenna 1 you have this sort of a phase lock loop architecture for recovering a sign of that particular frequency. Okay, what is a phase lock loop? You can think about it as an adaptive filter. Okay, so this is frequency domain. Remember the reference was a pure sinusoid, so it looks like an impulse, right? And it's buried in a large amount of noise. The PLL acts like an adaptive filter. It allows the reference to pass through, and it filters out a lot of the noise. Okay, now, unfortunately, what happens is that there is still some amount of noise remaining, right? This noise, it manifests as random phase modulation of the output. Okay, so instead of obtaining sine 2 pi fct, what you actually obtain is sine 2 pi fct plus theta, where theta is a random quantity that is governed by this nonlinear stochastic differential equation. It's not very important. This is just for completeness that I'm providing you. Okay, so you can actually analyze this system and characterize what the distribution of theta looks like. If you know the distribution of theta, then you can characterize what this quantity looks like and what its spectrum looks like. Okay, so once you do that, you know what is the spectrum of the output here. So then you know what is here. All you need to do is try and figure out what these integrator outputs look like. Okay, that is what we'll do next. Is the integrated outputs. This is the received reference signal multiplied by the in phase and quadrature phase components of the PLL output, right? This is the theta of PV hat. And if you do this calculation, you can show that it becomes something like this, okay? The integrated outputs, this is some noise, measurement noise, okay? And this is the intended signal. The integrated output is actually proportional to the channel at the frequency of C, and this is what we exactly desired. We wanted to obtain some quantity that's proportional to h of fc. Okay. So that is good, but the bad part is that this intended signal component, it decays exponentially with the variance of this theta. Okay. So this theta, or what we call as phase noise of the PLL, if it is small, then you get a good signal quality, you get a very good estimate of your channel. But if the variance is large, then this could be arbitrarily bad. You're essentially updating your phase shifters using your noise, which means your beam could be anywhere. Right? So what does this variance of this quantity look like? Well, the variance, you can analytically show that it becomes an expression something like this. All of these are constants. What you see is that it's inversely proportional to the channel at the first antenna. Why at the first antenna? Because we assume that the PLL is connected to antenna number 1. So if the input to the PLL is strong, that is the channel to this is good, then the variance is low. If the input is low, then the variance can be large. Right? So in a sense, what your system is missing on is diversity gain. You're only using one antenna to do the reference tone recovery. If that antenna has a bad signal quality, then you're done. Your beams could be arbitrarily bad. Right? So here is the claim. While the reference tone is actually being received at multiple antennas, right? So why not try to recover this sine and cosine using multiple antennas? Why only from one antenna? Okay, so that's what we'll do about next. Note that the reference tone is received at the different antennas with different amplitudes and phases. So it's not that you can just combine, add them up and feed it to a PLL. Okay. So one architecture that we'll be considering is something called a weighted carrier array. Okay. So this is again like a coupled PLL architecture. Here there is one primary PLL and then there are many secondary PLLs. Okay. So what is the role of the secondary PLL? Well, as I said, the reference tone at each antenna comes with a different amplitude and phase, right? This compensates for that phase. Okay, this compensates for those phases. And then these signals are then, once the phases are compensated, then you can actually add all of these signals up. And then your SNR increases. And that increased SNR signal is what is tracked by the primary PLL. Okay. The details are not very important, but essentially you can show that the variance of this phase noise now becomes a quantity that looks like this. These constants are the same. Here earlier we had the channel strength at the first antenna. Instead of that, you have a sum of the channel strengths at this script m, where script m corresponds to the subset of antennas where you're doing this sort of an arraying architecture. So in other words, you're getting like a maximal ratio combining gain because you are using signals from multiple antennas. Okay, so then you obtain these integrator outputs and you use them to drive your phase shifted arrays. And during data transmission phase, you are just sending data through those phase shifted array. So the outputs you can show if you are using OFDM transmission during data transmission, then you can show that the SNR on the kth subcarrier takes on this complicated expression. Okay. Well, the expression looks complicated, but what's interesting to note is that it scales linearly with the number of receive antennas, and this is what we precisely desired. You want a beamforming gain that increases linearly with the number of antennas you have, and this shows that. Okay, so let's briefly look at some simulation results. Okay, so we consider a 16x4 uniform planar array. These are some channel parameters. We assume that there are 3 paths arriving at your receiver, and then these are different parameters that are used for the PLLs. It's not very important. If you want, we can discuss about that offline. But this is what the results essentially look like. The green curve is what you get if you use conventional beamforming, but an oracle is telling you the correct channel information. So an oracle is giving you the perfect channel knowledge. Using that, you are building the beamformer. This is what you get. Okay. The blue curve, or rather the light blue curve, the dark blue curve is what you get if you are doing this sort of analog channel estimation based beamforming and you're using a PLL that's only connected to the first antenna. Okay, so as long as you are above a certain SNR, you actually do pretty well. You only lose 2 dB of beamforming gain. But when the SNR reduces, you do pretty poorly. Why are you doing poorly? Because remember that exponential term, right? The loss increases exponentially with the variance of the phase noise. So when the SNR reduces, that phase noise increases, and therefore you get this drop. Okay. The x-axis is not the SNR at the antennas, but it is the SNR that you would get if you had the full beamforming gain. Okay. So in other words, what I mean to say is that today's systems, they need that after the beamforming gain around 10 dB of SNR to operate. So this is the region of interest that we are looking at. Okay. Anyway, so because this performance gets pretty poor, when you use this arrayed PLL architecture where you are using the signals from multiple antennas, that's when you get this red curve. So you can do much better, right? This drop off happens at a much lower point. So this was the case where you used only a sparse channel. We assume that there are only 3 paths in the channel. What happens as the number of paths in the channel increase, right? So that is this curve. So we use the release 14 3GPP channel model, and this is the number of paths. And as you can see, as the number of paths increase, both conventional statistical beamforming performance goes down, and the analog channel estimation based techniques go down. But of course, the analog channel estimation techniques go down faster. Why? Well, because we are not adding the contributions from the different paths in the correct phase, right? And this is only a good technique when the number of paths are few. When the number of paths increase to infinity, in fact, it could be arbitrarily bad. So as long as the number of paths are few, you can actually use these techniques. And mind you that here the number of paths is slightly misleading. The number of MPCs should be rather treated as the number of clusters, because we assume or we treat each MPC to have several subpaths. According to these channel models, you have around 10 to 20 subpaths. Okay, so this actually, the x-axis actually corresponds to the number of clusters you have in your channel. Anyway, so these were the capacity curves when you did not take the channel estimation overhead into account. We saw that you get only a 2 dB degradation in your beamforming gain. So let's quantify the channel estimation overhead, right? So let's assume you're doing downlink training with feedback. Let's say now instead of having a single antenna at the base station, you have a multiple antenna array. You are training in downlink and getting some kind of feedback, okay? So you sweep your beams at the transmitter and you sweep your beams at the receiver, okay? So what you're doing is, you transmitter, you pick one beam and you transmit, then the receiver sweeps and sees if it acquires some power, then it will send a feedback, then you pick the next transmit beam, sweep, feedback, and so on and so forth, right? And so the base station, as I said, is doing this exhaustive beam scanning. Well, if you use conventional channel estimation, then you have to do beam scanning at the receiver as well. Right? You pick one and you. But when you're doing this analog channel estimation, you are no longer doing beam scanning at your receiver. The beam automatically adapts to the correct direction without actually having to scan beams, right? So then the feedback that you have to send is only 1 bit of whether that strength is good enough or not. So because you are no longer doing scanning here, the overhead actually can be reduced by a factor of 4 to 16 depending upon which technique you are using, which channel estimation technique you are using here. So you are able to reduce the overhead by a factor of 4 to 16, which is huge. Now, many of these advantages also hold during the initial access phase. The initial access phase is where the base station and UE don't have to discover each other, so they don't have timing and frequency synchronization. So many of these advantages also extend to that scenario. Okay, so in summary, when you have these reduced complexity transceivers and you're using digital channel estimation with them, the overhead is usually large because you cannot avoid the fact that you have to time multiplex your digital chains across the antennas. In this talk, I talked about one transceiver architecture that can actually acquire this required channel knowledge in analog. And the advantage is that when you do this, the overhead for learning the channel and for initial access becomes very, very small. A second advantage is that you can now acquire the timing synchronization with the full beamforming game. Now this is something that I had not shown explicitly, but essentially any of this beam alignment that we talked about, it doesn't rely on the fact that you have prior timing and frequency synchronization. Okay, so whatever timing synchronization you want to do, you can do after the beams get aligned, so you get the full beamforming game. Okay, so these schemes are also more resilient to phase noise at the transmitter. Why? Because you are using a PLL to recover this transmit sinusoid. So whatever phase noise is there, you are sort of trying to track it. Another advantage is that it's more resilient to MPC blockage. Now I'll discuss this in a little more detail. So what do conventional techniques do? If I'm doing conventional beamforming and if I have one path from there, one path from there, what I end up doing is I pick one of these two paths and I build a beam in that direction. Why can't I combine both paths? The reason you can't combine both paths is that whenever you're doing beamforming in analog domain, you have to do something that's frequency flat. You cannot bring frequency variations, right? So if you build a beamformer that combines these two paths, you can only make sure that these two paths add up in the correct phase at one frequency. You cannot ensure that they add up with the correct phase in all frequencies. So the best thing to do in the capacity sense is to just pick one of these two beams. This is good, and this is why you get that 2 dB gain over what we were doing. But the disadvantage of that is that if that path gets blocked, then you go into outage, and then you have to search till you find the other beam. Right? In this approach, unintentionally we are combining power from these multiple directions. Right? This is bad because, well, obviously you are not able to add all of them in phase at all frequencies, right? So you get the 2 dB loss. But if one of the paths gets blocked, you still have resilience. You can get signal from the other component. So you have sort of diversity against MPC blocking. Okay, so these were some of the advantages. Let's talk a little bit about the issues. Okay, firstly, the cost of analog hardware increases because now you are using additional blocks to do this sort of channel estimation in analog domain. Second thing is, this technique only supports a single spatial stream, right? Why? Well, it's not like if from the transmitter, if I have one path from there and one path from there, I can send one data stream through this and one data stream to this. Why? Because in analog, you cannot distinguish between this beam direction and that beam direction. It cannot understand what these two different directions are. This very limited capabilities that you have in analog, right? So you can only support a single spatial stream. Thirdly, when you have these multiple paths, because they are not adding up in phase, you get that 2 dB beamforming loss. Okay. Now, in fact, all of these three issues can be resolved. We are actually working on a better architecture where the cost of hardware reduces, you can support multiple spatial streams, and that loss in beamforming gain can be brought close to zero. Okay. That's not the focus of this talk because that's still ongoing work. But I'm just letting you know that can be done. So, some future direction. So, till now, we have not looked at interference, right? So it will be an interesting study to see how this system performance gets affected when you have interference, and how would it perform in actually measured channels as opposed to simulated channels. Interference is actually important because why? Well, if you know the concept of pilot contamination, where if this base station is sending some pilots to train the user, and another base station is using the same pilot, then the user learns the channel to both the base stations. Similarly here, if two base stations are using the same reference node to train their particular cells, this mobile will learn not only the beam to this, but to that as well. So things about how you want to tackle that are something that you would like to look at, right? And there are many phase noise mitigation techniques that have been used in the past. So it'd be interesting to see how those can be used to actually improve that dip that you were getting in performance. And more detailed analysis on time and frequency synchronization with these techniques has to be considered. Okay, and this is something that we already have a solution to, is how to reduce the hardware cost and multiple spatial data stream transmission. And one last question, which is much more interesting, would be what are the fundamental limits of what you can do in analog? Can you say that it's always going to be worse than digital? It's not clear yet that it's always better than digital or not. There's very little work in this, so something that has to be looked at in more detail. Right. So these are some of the patents and papers with respect to this work, and these are some previous papers. Yeah, thank you.